In this video, we'll go over line integrals of vector fields. So if you think back to your various physics courses, you might be familiar with the concept of work. So the work is a form of energy, right? So the work done by a force acting on an object to move it in a straight line can be calculated as W equals F dot D. This dot is supposed to be a dot product. However, this motion, again, is just in a straight line. So we want to extend this concept to calculate the work done when an object moves along a curve C in the presence of a vector field. So to visualize sort of what we mean by this, there's a diagram at the bottom of the page here. So the blue vector lines are supposed to represent the vector field, and this pink curve is the curve C, right? So imagine you have an object that starts at this point and it moves along the curve and ends up at this point here. So the vector field is acting on the object at every single point along the curve, and depending on how the vector field lines are pointing in for each point, it may contribute more to the work or it may contribute less, right? So in the instance where the vector is parallel to the direction of travel, it contributes a lot to the work. However, if it's perpendicular to the direction of travel, then it doesn't contribute anything to the work, right? Because the dot product is zero when two vectors are perpendicular. Okay, so that's the idea that we're trying to calculate with this kind of line integral. And so how we actually perform the calculation is described here, right? So we have a vector field that's continuous. That just means that the components of the vector field are continuous functions, and the curve C should be smooth, or at least piecewise smooth. And so if we parameterize the curve C with this vector function R of t, then we can set up the line integral of the vector field through this ordinary integral described here, right? So we integrate from a to b, so that's just for the parameter t, and this f of r of t means, what this means is that your curve r of t has components xy or xyz, and so you should plug those components into your vector field so that everything is in terms of t. And then this being a vector, you can calculate a dot product, and this is just r prime, which we are familiar with from previous chapters. Okay, so you take this dot product, the result will just be a function of t, and then we can calculate the ordinary integral with respect to t. So that's the basic setup. So to be more specific, say you have a two-dimensional vector field, right? So your vector field will have two components, say p and q, and your curve C again has two components, the x component, the y component, and so here this vector field is represented by p and q, but as we said before, you have to take the x and y components of the curve and you plug it into p and q so that everything is in terms of t here. And then here this is just r prime, right? So then you calculate this dot product and then you proceed to calculate the integral with respect to t. So again, that's how we calculate these kinds of line integrals. Sometimes so most of the times I'll write the integral in this form here, but sometimes an alternative way of writing out this line integral is written like this, where you separate the p and q components like in this way here. Basically, this notation is equivalent to this notation, right? Because if you actually carry out this dot product, what does it look like? P times x prime plus q times y prime dt, right? And then you just replace x prime dt with the differential dx, and then y prime dt with the differential dy, and then you get exactly this expression here. So these two things are equivalent, and so sometimes it's written like this, sometimes it's written like this. Okay, so that's a line integral for two-dimensional vector field, and so for a three-dimensional vector field, it's very similar, except the vector field f will have three components, p, q, and r. Your curve is in 3 dimensions now, so you have x, y, and z components, but the setup for the calculation follows a similar procedure, right? So the x, y, and z components should be plugged into the vector field here so that everything is in terms of t, and then you calculate this dot product, and then you calculate this integral. Okay, so that's the basic idea behind a line integral of a vector field.